drop it on the chat or mute yourself. Yeah, welcome, Timo.
Okay, thank you very much, Nana. Good afternoon, good evening, good morning, everybody. Thanks for joining. And first of all, big thank you, of course, to the organizers for organizing this great event. It's been really very inspiring for me, and I've learned a lot. And I'm also very grateful that I have this opportunity to present these recent works with Songju Lee, Wolfgang Lerche, and at least on one slide, I'll also give a brief overview of this work with Rafael Alvarez Garcia and Daniel Kleber. So it's the aim of a longer problem, as we all know, to try to understand what the Swampland distance conjecture of Oguri-Waffer means, which is the statement that at infinite distance of a quantum gravity, an infinite tower of states should become exponentially light. As we heard yesterday in the very interesting discussion session, this is an exceptional claim, and exceptional claims need exceptional evidence. Luckily, I think for the Swampland distance conjecture, there's plenty of evidence, probably two types of evidence. The first type of evidence is by inspection in string theory, and particularly clear such type of inspection can be done for the case of complex structure moduli limits in type 2b on Calabi-Yau threefolds. This would be limits in the vector moduli space of the corresponding 4D n equal 2 supergravity theory. And there, in a number of works, the emergence of this tower of light states has been proven, has been shown. The states in question are the three branes wrapping certain vanishing special Lagrangians whose calibratic volume vanishes in the limit. And there's a beautiful mathematical story behind the theory of limiting mixed Hot structure, which of course has attracted a lot of attention in the literature. The second type of evidence would be bottom-up evidence. And recently, ideas have been put forward to try to connect the distance conjecture to entropy arguments, to black hole arguments, similarly, not similarly, but in a parallel vein of what has been done for the weak gravity conjecture. The content of this talk, however, is more the question, what is the nature of the light states and the asymptotic physics? And I insist on this question because I think that it's a very important conceptual question. It might help us to answer some of the conceptual questions behind the Swampland distance conjecture and interpret the asymptotic properties of quantum gravity in this context. So if one knew the answer to this question, I'm sure this would shed a lot of light on the interesting emergence proposal. It would maybe tell us much more about the origin behind the weak gravity conjecture, at least in the limit of small coupling. So maybe give the reason why the weak gravity conjecture has to hold. And ideally, of course, could also tell us something about asymptotic cosmology, the focus here being on the word asymptotic, of course. So that's why I like to think about this question, and a proposal or conjecture for an answer, a potential answer is formulated in the emergent string conjecture, which makes explicit this idea that underlies the Swampland distance conjecture and has always underlined it, of the importance of dualities. Namely, the statement would be that the parametrically leading tower of states becoming light at infinite distance is either a dual KK tower, in this case we have a decompactification limit, or it's the tower of excitations of a asymptotically weakly coupled fundamental string together with the KK tower. So in particular, the statement is whenever you don't find a weakly coupled fundamental string becoming light, then the tower of states that you get, no matter what complicated they are, should have an interpretation as a KK tower, at least as far as the leading and parametrically lightest tower is concerned. That at least is the claim. For this claim, we also have a lot of quantitative tests within string theory, admittedly, string or M theory, mostly in the Kähler moduli space. And these tests have been performed in various dimensions with varying amount of supersymmetry, 8 supercharges, 4 supercharges, most recently discussion on 0 supercharges. The emergent string conjecture is also related to the interesting distant exonic string conjecture, as we learned in Luca Martucci's talk yesterday. The emergent strings would be what they call the W=1 subcase of the EFT string. So for details, I refer you to this paper or to yesterday's talk. by Luca. And the goal of this talk is to try to challenge the emergent string conjecture. So the original idea was that maybe one could find counterexamples by looking into types of constructions which are not of this Kähler moduli form where the conjecture seems to be well behaved. The first question one could ask is, does the interpretation of the states as KK states or string excitations uphold in more abstract types of moduli spaces? Most importantly, what about the complex structure moduli space that has been studied so much in detail already? And what about open string moduli, quote unquote? And a second way to possibly challenge the conjecture would be to think, could there be higher dimensional fundamental objects, not just a fundamental string becoming light, but maybe at the parametrically leading scale, something higher dimensional in the sense of a fundamental object, whatever this means. So these would be two questions one could ask. So in the main part of this talk, I will be addressing the first question within a particular framework. Namely, I'll be studying infinite distance limits in complex structure moduli space of F theory on elliptic K3 surfaces. So on the one hand, this is the complex structure limit now. On the other hand, this also geometrizes, as we know in F theory, certain, among other things, certain open string infinite distance limits. So a different type of limit that was considered so far. And as is appropriate for this conference and for this workshop, I hope this analysis comes in two parts. A geometric analysis. I will advertise a refined classification of the infinite distance limits for elliptic K3 surfaces. So this is a purely geometric result. And then from the Swampland perspective, try to interpret the states which become light and put them into the context of the emergent string conjecture. And indeed, we claim that we find agreement with this interpretation of the states which do not come from strings as Kaluza-Klein states. And the take-home message of this part of the analysis for me are that it's really important to take into account all the towers at the parametrically leading scale in order to read off the asymptotic physics. That probably goes without saying. And second, that indeed effective Kaluza-Klein towers often come in disguise. So towers which may not look like Kaluza-Klein towers in the particular formulation that one looks at might have a dual formulation as Kaluza-Klein states. And we will give another example where this is happening. But before I come to this main theme, let me very briefly address this other potential challenge of the emergent string conjecture. Could there be other higher dimensional fundamental objects becoming light at the leading scale? And in this paper, we claim that in a certain sense, this is not so. So we claim that there can be no infinite distance limits in which the scale of a fundamental membrane becomes parametrically leading. In particular, if, say, the KK scale scales to 0 in this fashion, 1 over m mu cubed from mu to infinity, then the scale of the fundamental membrane goes to 0 much slower. Whereas fundamental membrane, this is, of course, a delicate issue. What we mean by this, we here mean a membrane which, upon circle reduction, reduces to a fundamental string. So not just to a non-critical string or any other strongly coupled string, but really to a fundamental string under S1 reduction. And we argue that this claim follows already by consistency of the emergent string conjecture under dimensional reduction. Dimensional reduction, of course, is a topic, and consistency under dimensional reduction is a principle that has been applied many times in the Swampland context. And second, we somewhat independently argue that this principle indeed upholds very concretely when we look at infinite distance complex structure moduli degenerations of M theory, compactified to 5 dimensions. This is the 5-dimensional hypermultiplet moduli space. And in fact, we heavily rely here on previous results by Bohr-Marchesano-Wiesner, who studied certain 4D emergent string limits. So this just as an advertisement, if I may, and I'll be happy, of course, to discuss this later. But now let's come to the point of this talk. And I will first start with the geometric analysis, namely try to give a classification of infinite distance limits in the complex structure moduli space of elliptic K3 surfaces. And these elliptic K3 surfaces are, of course, the spaces that define for us F theory in 8 dimensions. And I'm here taking only the purely geometric perspective. So I only look at F theory in 8 dimensions without any possible background fluxes, like freezing of singularities and so on switched on. So the conventional simplest case, if you think. Just to fix notation, a quick reminder of what we need. We will not need much on the elliptic vibrations. All we need is that they can be described by a Weierstrass model, which of course we all are familiar with. The Weierstrass model is defined in terms of two functions, f and g, which are functions on the base, or more precisely, certain sections on the base of the compactifications. The space is the of the elliptic vibration. The space is the compactification space. The 7 branes are points on this base and fill 8 dimensions. And the points are characterized by the vanishing of the discriminant delta, which is this combination of f and g. And as we all know, from the vanishing orders of f, g, and delta at various points, we can read off the algebra on the 7 branes, the Lie algebra. This is the famous Kodaira classification. Again, details are not necessary. The only thing that is necessary is to remember is that this classification stops as soon as we reach vanishing orders 4, 6, and 12. Okay, so we take this most general framework of a Weierstrass model over P1. Every elliptic vibration with section can be written as such a Weierstrass model, so we lose no generality in assuming this. And now we want to study the degenerations in complex structure moduli space at infinite distance. And for simplicity, I'm only looking at one parameter family of degenerations. So there will be one complex parameter which takes values in a disk on which f and g and therefore the elliptic vibration depends. So it is useful, in fact, to view the setup, this family of degenerations, as a threefold by itself. Namely, we have here the disk, this blue object in which this parameter takes values, and for every value of the disk, we have a particular K3 surface. The generic member of this family is a smooth K3, so this would be a Weierstrass. This would have a Weierstrass model with Kodaira type fibers. If we resolve the fibers, the singularities, then we get a smooth K3. And in the center, we have the degeneration that we are interested in studying. And we are interested in the infinite distance degenerations, the potential infinite distance degenerations. And we know that these can only be one of the following two types. So either it can happen that for u equals 0, the fiber over in the elliptic vibration degenerates everywhere, over every point. These would be the Codimension-zero degenerations, for which this discriminant vanishes at u equals 0 over every point on the base. Or we could have non-minimal degenerations, where we have at a point on the P1, but for u equals 0, for this value of parameter u equals 0, a singularity of type 4, 6, 12 or higher. Indeed, everything else is captured by Kodaira and is known to be at finite distance. So let's look at these two cases in turn. The first case is a bit boring. Let me just briefly discuss it. So we want a degeneration where the fiber over the P1 degenerates everywhere. And in fact, without loss of generality, one can assume that this degeneration is of what's called IN type. This means that f and g do not vanish for u equals 0, but the discriminant vanishes, but it vanishes at u equals 0 over every point of the base. Indeed, one can easily argue for this by base change and rescaling. I'll be happy to bring the argument later if you're interested. Now, this means that the interpretation is very clear. What happens is that the exodilaton in this case goes to I infinity over every point of the base. So GS, the string coupling, goes to 0 everywhere on the base manifold. This is a weak coupling limit. In fact, this is familiar from the famous Zen limit, of course. This is a type of weak coupling limit. And this is what one would call an emergent string limit, where the weakly coupled type 2b string becomes the important object. We'll come back to this in a second. But here, let me just note that for the simplest case, for instance, where we take n equal to 2, we would have an I2 fiber everywhere. This means a fiber which we can resolve into two P1s which intersect, and they form this type of vibration. And in the F-theory literature, such type of infinite distance degenerations, with a focus on infinite distance degenerations, have been appeared, for example, in this paper by Morrison. So this would be the case, Codimension-zero degenerations. We expect something like a weak coupling limit. Now, the more interesting case for us will be the second class, namely non-minimal degenerations over points, meaning if I take u equals 0, my parameter u equals 0, then over certain points, let's call them s equals 0 on the base, we have vanishing orders fg delta, which are 4, 6, 12 or higher. Such degenerations cannot be dealt with directly, but there is a trick, which again has been discussed in physics literature, for example, in this Aspinall-Morrison paper and many after. What one can do is one can blow up the point where this happens, and I view this point now as a point in this threefold given by the K3s together with the disk of its parameter space. Now the blow up is simple. I can do a simple toric blow up and rescale. I therefore introduce a P1 at this point of over which we have this 4, 6, 12 vibration. And I can iterate this well-known procedure until no non-minimal singularity is left. And the result is that the fiber here at over u equals 0, so the degenerate K3, now degenerates into a union of different surfaces, like shown here. Each of the surface components, Yp, is by itself an elliptic fibration, which may be degenerate. So the base has been replaced, the P1 has been replaced by a chain of P1s, and there can be P many of them. P can be an arbitrary value depending on the degree of degeneration. So that's the general procedure. And now the question is, what can happen? What comes out? What are the possible types of chains of such surfaces that we can head at infinite distance? And second, how do we interpret their physics? Because these look pretty bad from a physics point of view. How do we do F-theory on them? So let's first ask the question, what can happen? So this is a longer analysis, and I'm only giving the results. It turns out there are 3 possible outcomes. And the outcomes can be characterized already from the point of view of the Weierstrass model by looking at the vanishing orders at this point, which goes beyond 4, 6, 12. Namely, if all that happens is that the vanishing order of the discriminant is exactly 12, then we get the first class, which we call type II-a. If the vanishing order of the discriminant is bigger than 12, but those of f and g are just 4 and just 6, we get a second class, which we call type III. And the most mysterious case, when the vanishing orders are strictly bigger, 4, 6, and 12, then we can either get type 2 or type 3 as above, or finite distance. So what does this mean? What this means, I am going to tell you now. For now, I just need you to remember there are 3 possible cases depending on the vanishing orders of f, g, and delta that one can classify. So let's look at these 3 different cases in turn to see what the geometry is and then what the physics will be. First case, this is the case where we have a vanishing order 4, 6, 12. So discriminant exactly 12. It turns out when you do all your blow-ups, you get a chain of surfaces which intersect. So instead of a single K3, we now have this chain of different elliptic vibrations. The chain has 2 end components on the left and on the right. These end components are both rational elliptic surfaces, so DP9 surfaces with 12 singular fibers. And the surfaces in the middle are just trivial vibrations, a direct product of a torus with a rational curve. We can therefore blow down these middle components, if we like, to a single point. And at the end, what we get is something that always looks like shown here on the right. We have 2 elliptic vibrations over 2 P1s, which intersect in a point. And we have 12 branes on the left and on the right. So instead of the original 24 branes of on K3, we have now 2 pairs of 12 branes, one on the first elliptic vibration, one on the second. These are DP9 surfaces. They intersect in a point. And this, of course, to an F-theorist is something very well known. It's the famous stable degeneration of Morrison-Buffer that describes the dual heterotic string in the large T limit. So this is an old friend that one recovers. Nothing earth-shattering. Let's now go to the remaining cases. And these are more interesting, and these were not known in the physics literature. And these are the cases called type III. This means that the vanishing order of the discriminant is bigger than 12, strictly bigger than 12. Again, we will get a chain of surfaces, and we need to deal with the end components of this chain and the middle components. And from there, we can read off the physics then. So the end components can be one of two things. It can either be, again, a DP9, a rational elliptic surface with 12 singular fibers, or it can be a surface where the exodilaton goes to I infinity over every point. So in other words, where again, we have a degeneration over every point of the surface. And in addition, we can have extra 7 branes on specific points, and these can correspond either to A-type singularities, this would be an extra SUN gauge group, or to D-type, this would be an extra SON gauge group. And this is all there can be. And on the N component, there must be precisely 2 such D-type singularities. So that's just a list of properties that one can prove to hold. The intermediate components, on the other hand, all have generic IN fibers, and they can have enhancements only of type A. And what this means is that on each such intermediate component, one has a locally weak coupling regime. So a picture says more than 1,000 words. Let me show everything that I said. Unfortunately, it doesn't fit on one page. That's why I first had to make the words and then show the picture. So these are the cases that can occur. I'll say it again. So the K3 becomes a chain of surfaces which intersect. On the middle components, the fiber degenerates everywhere, and GS goes to 0 over every point on the middle components. On the end components, either we have something like a DP9 on both sides, or we have one DP9 and something where the fiber degenerates everywhere. But then there must be 2 D-type singularities. These would be O-planes in physics language. Or type 3b, we can have 2 of those guys with the weak coupling regimes in the middle. And this is all that can happen, as one can show explicitly. So that, in fact, concludes the classification part. Let me just briefly say how this fits into the math literature. So, of course, it has been known for a long time, or the theory of degenerations of K3 surfaces in general is a classic and rich topic in the mathematics literature. And according to a number of theorems, every 1 parameter degeneration of general K3 surfaces, not necessarily elliptically fibered, every such degeneration is one of 3 types called Kulikov model type 1, 2, and 3. The type 1 models are the ones at finite distance. So this is where Kodaira's singularities would live. And the infinite distance ones are of type 2 and 3. They are all of the type that we have various surfaces that intersect in a complicated way. In type 2, the intersections of 2 surfaces are tori, and in type 3, the intersections of 2 surfaces, if non-zero, are rational curves. This is how the Kulikov models are defined in the mathematics literature. And more was known, namely in the case type 2, there are precisely 2 possibilities up to certain birational invariants. Namely, we can either have the situation that looks like a stable degeneration, a la Morrison buffer. This was what we got from resolving the 4-6-12 point, so 2 DP9s intersecting. Or we can have something that looks like a global weak coupling limit, like a SEN limit. So a situation where the fiber degenerates over every point of the base, and we have a weak coupling limit. And these are the only 2 possibilities that can arise of type 2. And indeed, we found them via the direct Weierstrass analysis. Now, as far as the type 3 models, a corresponding analysis had not been done. More precisely, we can now look at elliptic K3 surfaces and their Weierstrass models. That's exactly what the framework that we've been looking at. And what I just told you is essentially classification results. It tells us that all the elliptic K3 degenerations of this type 3, so all the other ones, come from Kulikov Weierstrass models of this type, either 3a or 3b, precisely the ones. So we have, and we know how to construct them explicitly from the Weierstrass model, and we know that that's all there can be. And when I say this was not known before in the literature, then I mean this was not known in the literature until this very recent work. Our results are independent. In fact, I must confess, I was not aware of these works when we were starting the project and doing most of the analysis. Our results are compatible with them, but use very different techniques. Of course, the mathematicians wouldn't maybe start from this Weierstrass model, and they use very different techniques. But as far as I can see and understand, the results are compatible. Okay, so this was the first part. Classification of infinite distance limits, 1 of 4 types, 2 of which were known, and the other 2, 3a and 3b, are new. And now let's come to the physics part, the Swampland interpretation. In what sense do these infinite distance limits now give rise to an asymptotically massless tower of states? What's the nature of those states once we consider, for example, F-theory on those geometries? Already from the general theorems, we know a large part of the answer, because it's known by general arguments that these Kulikov type II and type III degenerations have respectively 2 or 1 transcendental torus whose volume becomes 0 in the infinite distance limit. So it's known that in a type II degeneration, there must be 2 tori, which are not holomorphic curves, so transcendental tori whose volume goes to 0. And in the type III case, there must be precisely 1. This was known on general grounds. And if we now consider M-theory on those bases, for example, we would clearly expect 2 in the type II case and 1 in the type III case towers of asymptotically massless BPS particles by wrapping M2 branes along these vanishing cycles. And in fact, the fact that these are tori means that they can be wrapped arbitrarily many times. So we don't get just a single BPS state, but we get a full tower of states, 1 for each of the tori. And this reasoning is, of course, completely analogous to the more general arguments for Calabi-Yau 3 and Calabi-Yau 4 folds that I briefly reviewed on the first slide in these works. In the present case, at least, however, these M2 branes associated with these tori in general form only a subset of the asymptotically massless states, and in general only a subset of the leading asymptotically massless states. So one has to be careful to find all the towers at the same scale in order to extract the asymptotic physics. And this is what I'm trying to do now. Let's start with the simplest case. This was the simplest of the 4 cases, was this Kulikov Type II.a model, the stable degeneration limit, the famous stable degeneration limit. So it's a type 2, so there should be 2 tori that become of 0 volume at infinite distance. So how do we construct them? Geometrically, we can construct them as follows. We combine one of each of the 2 1 cycles in the fiber, the A cycle and the B cycle, combine it together with the pinching 1 cycle that pinches at the intersection point of the 2 P1s. And this cycle is precisely this green cycle sigma denoted here. Combining these, we get 2 tori, gamma 1 and gamma 2, and the volume is 0 because the cycle sigma pinches to a point. So what would now be the interpretation of the corresponding 2 towers of states in F-theory? Well, an M2 brane wrapping on SA and SB respectively gives rise to a 1-0 string or 0-1 string, which now in addition has to be wrapped on this 1 cycle sigma that pinches at P. So we get 2 string junctions, a 1-0 junction and the 0-1 junction, which encircles the point P. And this can equivalently be seen as encircling the 12 branes on, say, the left DP9, or equivalently the 12 branes on the right DP9. Indeed, this is possible because these 12 branes have an SL2Z monodromy, which precisely multiplies to the identity matrix. So therefore, we can have precisely 2 types of string junctions encircling all the branes, a 1-0 junction and a 0-1 junction. Now, this monodromy matrix is the same monodromy matrix as the double loop algebra het E9, which is a loop extension of the affine algebra het E8. This is the algebra that one gets by combining all the 12 branes on one of the DP9 surfaces into a single algebra. So the picture is that the 4-6-12 enhancement originally placed 12 of these branes on the left and 12 of these branes on the right into one point. This gives rise to these to the so-called double loop algebra. The blow up just resolves them artificially in an artificial geometry, but one can still see the origin by realizing that the states that the junction that encircles all these coalescing 12 branes indeed are massless in the sense described. And now what's so this gives the geometric picture for the states. And what's now their physical interpretation? We claim that these are precisely the Kaluza-Klein modes of the dual compactification from 8 dimensions to 10 dimensions of the dual heterotic string. And this is clear because that's what the stable degeneration limit does. And one can show this in more detail by looking in detail at the heterotic dual. But in any case, this loop algebra enhancement is indicative of such a circle decompactification, in this case, 2 circles. So this was the first model, decompactifications 8 to 10. The second are these recoupling models. Here, things are a little bit more complicated. I want to be only very brief.
Sorry, Timo, can I have a quick question about the previous slide?
Yes.
So when you say that the dual head, so in that limit, what is the lightest string? Is it a perturbative type 2b string description or a heterotic string description?
The type 2b, the heterotic will be the lightest string, but
okay.
but heavier than the KK tower.
Okay, but in terms
on the
of
heterotic side,
string theory, then there would just be normal Kaluza-Klein modes. So yeah.
In the dual heterotic, these are normal Kaluza-Klein modes. Exactly. That's just a volume of the torus, of the dual heterotic torus going to infinity. Absolutely.
Okay.
It's
but
just
the heterotic string is lighter than the 2b string in that limit. So that's, I mean.
Yes. Yes.
Okay. So they are normal.
Exactly.
Okay.
The heterotic string in the dual limit will be should be lighter. But the KK tower is even lighter. That's why.
Yeah, that's fine. Yeah. Okay. Great. Thanks a lot. Yeah.
Okay. Thank you. Thank you. So the second type, it's a little bit more complicated. I want to be only brief. So this is this recoupling limit. So let's think for simplicity of the Sen limit, where we have an I2 degeneration everywhere. This means GS goes to 0 everywhere, and we resolve this I2 into these 2 P1s. And the point is these 2 P1s intersect in 2 points, but these 2 points are exchanged. This means that the intersection of these 2 P1s in the fiber is really a double cover of the base, which in fact turns out to be a torus. And what we can now do is we can combine the shrinking 1 cycle SA, which shrinks at these intersection points, with each of the 2 1 cycles of this torus E. So it's maybe not very intuitive. This gives us, again, two tori, gamma 1 and gamma 2. And the interpretation is, again, in M theory, giving rise to massless PPS states. And this is important, in addition, one now does get a light string. Namely, one can also wrap the M2 brane just on the cycle SA, which shrinks to 0. So this also gives a string, which is also light, and in fact turns out to be, at the end of the day in F theory, at the same scale as the PPS states before. So the interpretation here would be really as an effective 8-dimensional limits, where we have a light type 2b string, and at the same scale, a light, 2 light towers of, say, winding strings, which come from just wrapping the string on the 1 cycles of the type 2b torus, which, however, doesn't undergo a further degeneration. So this would therefore be an effective theory in 8 dimensions. And here it's important to know that there was really this extra type 2b string, which also becomes light. That's what I meant, that one has to take into account all towers at the same parametric scale in order to not misidentify this as a decompactification limit, as otherwise one could have done. Okay, I'll be done very soon. Next, physics of type 3a. This is the new part. It's very similar to the stable degeneration, with the exception that instead of being able to wrap both the SA and the SB cycle over the combining it with this pinching sigma, we can only combine one of them, namely the cycle SA. This is because the other cycle, the cycle SB, would not survive the monodromies of the branes. One can show this. So from the type 2b perspective, we have now only a single junction of strings, namely the junction of strings which encircle the branes, say, on the left end component. And this, in fact, leads to an enhancement, again, from your gauge algebra to an affine algebra. In fact, the affine algebra E9 E hat 9 minus n for various values of n. And we interpret this once more as a decompactification limit from 8 dimensions to 9 dimensions, something that is already clear from the fact that we get an affine algebra. But once more, the detailed heterotic analysis that we do confirms this explicitly. One can map the degenerations of the Weierstrass model directly via certain mirror symmetry into Siegel modular forms that depend on the heterotic complex structure and Kähler moduli, and check that indeed we get a partial decompactifications from 8 to 9 dimensions. And the reason are precisely these encircling one cycles, these encircling junctions, which are this one tower of states that one gets from the Kulikov type 3. More precisely, this is true in type 3a. Let me just say very quickly, since from each of the end components to the left and the right, as long as it's a DP9, one gets such a affine algebra, one can determine the full symmetry of these compactifications and classify the possible maximal enhancements. And this, in fact, reproduces the previous results on classification of the rank 17 maximal non-abelian gauge algebras in 9 dimensions. I'll be happy to say more if you like, but in the interest of time, just this very last case. This is the fourth case, the model of type 2b. Here we have GS going to 0 on each of the component. We have two O-planes on the two end components. So this is a globally weak coupling limit. Indeed, we get a master string from wrapping the M2 brane over the vanishing one cycle in the fiber. So this is now a globally well-defined string whose tension goes to 0. So we get a string limit. But in addition, we get another tower of states, which is localized at the intersections and which is parametrically lighter than the string state. We can think of this as a degeneration of a type 2b limit in the limit where the complex structure modulus of the type 2b torus goes to infinity by itself. So this is a decompactification to a weakly coupled type 2b in 10 dimensions, or maybe dually then type 1. Okay, let me wrap up. We presented a refined classification of the infinite distance complex structure degenerations on elliptic K3 surfaces. And these, in fact, are in one-to-one with the possible infinite distance limits in complex structure moduli space of F degree on K3 with no fluxes. There are 4 such limits. They are either decompactification limits or emergent string limits, in the sense of just having a weakly coupled string becoming light with no lighter Kaluza-Klein tower. So once more, the message for me at least was that Kaluza-Klein states in a certain frame, in fact, can come in disguise, and particularly here the M2 branes wrapping the 2 tori, in some cases, as discussed, should really be interpreted as Kaluza-Klein states, or from the type 2b open string point of view as string junctions, which leads to affine enhancements as the hallmark of such a decompactification limit. Thank you very much for your attention.
Thanks, Timo. Yeah, for the very nice talk. So we have some time for questions. Ling.
Hi, Timo.
Hi.
Nice
Hi,
talk. Yeah, I had a question regarding the uplifts. How should I say this? So the affine, the delta junction that you expect from having these affine algebras, right? They correspond to a particular transcendental torus, if I understand correctly.
Exactly.
Exactly. And so okay, right. And I think in the dual heterotic picture, right? If you think about the winding and momentum states of the heterotic string, then you expect that there's, in terms of these Narayan lattice, you expect there to be a hyperbolic rank 2 lattice to sort of decouple if you uplift from 80 to 90. So in some sense, there should be like a dual kind of junction in this picture that is complementary.
Right. That would then be the winding strings. Right. Because these are the KK strings, the winding strings. They would be very heavy, of course.
Right.
So that is a good question. I don't see them here, to be honest.
Okay. So from this kind of M2 brains or wrapping some cycles, it's not obvious what they should look like.
Not now. In fact, I did think about this, but I think I forgot the answer. So right now I cannot point you to it, but I will think about this again. But it's absolutely true that this is one of these two possible hyperbolic factors. So in the type 3 case, only one of them appears. In the type 2 case, both of them appear.
Right.
Yes.
Right. Okay.
And that would be the interpretation. Yeah. So from just wrapping M2 brains, I cannot see them, I must say, because one could. Yeah. Indeed.
Okay. Thanks.
There's a question by Ivano.
Ivano, yeah.
Yes, hi Timo.
Hi.
Thanks for the very nice talk, as well as the reference. So I was curious about the quantitative behavior of the masses of the light states with the distance. Namely, is it important? Do we care that it's always a precise exponential or something else?
I think we do care, but we didn't do this analysis here. I think I would certainly care that it's an exponential, of course, to be in line. In the present case, since we have the heterotic dual or the type 2b description, in both cases it's clear that this is this exponential behavior.
I agree.
Because that's the behavior for the KK states of the dual heterotic torus, of course, and it's certainly also the behavior in the recoupling limit. So there's no question about this. But of course, you're asking how can you compute this directly from the F-theory point of view? And in principle, you can. And they're using these other types of techniques in supergravity, or this mixed hot structure technique would, of course, also be perfectly suitable to do this. So I view this really as a complementary view in order to make explicit certain aspects. Yeah. But absolutely. So we didn't do this quantitative analysis of the masses here because of the simplicity of the framework. But in other cases, one might want to be more ambitious. I fully agree.
I understand. Thanks a lot.
Okay, great. So there is another question by Paul, but we are a little bit constrained with time. Is it quick?
Yeah, I can ask really quic.
Okay.
Hey. Okay. So then I had two questions, but then I just ask one. Do you have any idea why? I mean, just from a general perspective, why you can only uplift to the heterotic E8 string, and not say the SO32?
The SO32, I think, is then contained in this type 3b limit by duality, because this would actually go to a type 1. If you T-dualize again. Yeah, I think this is where the heterotic where the type 2b is excuse me, where the SO32 would be sitting. So it's if I may just, I mean, I know we have a little time, but if I may go here. So we see in these limits, so there's one limit, the one to the left and the one in the middle, where we have dp9s on the very left component. And dp9 always means mutually non-local branes. And this automatically means E8, so that's the E8 string. But the one on the right, there we precisely do have only 4 d-type singularities, 2 + 2, together with this recoupling behavior. This is where where I directly go to type 1, and then by S-duality, this would be the SN32 regime. So in that sense, it's also covered, I would say.
Okay, that actually sort of answers the second question. Okay, good. Thank you.
Thank you. Thank you.
Okay, great. So we thank Timo. If there is another question, in fact, in the chat, but I would say that can be replied on the chat or later in the conference dinner. So I remember you all that after the last talk, there is 1 hour in Gather Town for conference dinner. So thanks to Timo again.
Thank you.